Okay, now this is the circuit that we have already established, and let's just do a little circuit analysis here to explain what the circuit was doing under the loaded conditions of the motor on the previous video that I did, and then we're going to look at how we can improve this circuit to get better performance of torque control for the motor under stalling conditions. Okay, so going with a little analyzation here now, we already know that this is our regulator on this side here feeding our feedback circuit here. This is the part of the circuit that we're interested in analyzing right now. Okay, so under normal running conditions, when the motor is running under normal conditions, we have current flowing from the regulator here down through this here output transistor here, motor driver, through the motor down to ground, and the motor's running properly. At the same time, we have a small amount of that current also flowing. Now we're going with conventional current flow still. Signal current flowing into the base of this transistor, causing this transistor to conduct and put a voltage at the base of this transistor, causing this transistor to conduct and to place a voltage and a current output to these two transistors to keep the motor driver running properly. Now, under the stall condition, when the motor begins to get a load on it, we begin to stall the motor, what we have is we have a decrease in voltage across the motor here due to the fact that the resistance of the motor begins to decrease. We begin to get a ground signal now applying across the motor, and so when that happens, we now get a low ground signal to the base of this transistor here, causing this transistor to conduct less now, which in turn allows this transistor now to conduct more, which sends more current out to the driver transistors to allow them to open up and to drive more current in the motor to pick up for that stall. And that's what we've seen. We've seen that when the motor was stalling, that the voltage at this point here of the series pass transistor on this feedback regulator here began to increase. It was increasing as the current from the motor began to pull current from the base of this transistor, and that's how that was increasing. But the problem was that we were not getting enough current pull from this here to drive the motor back up and to get the voltage across the motor to increase back over it again. Instead, it was still, the voltage was still dropping across there due to the fact that we weren't getting enough current flowing through here. Now I'll show you what circuit I came up with to remedy that and to cause this motor to have better torque control now under that condition. Okay, now the first thing I did whenever I began to work on this circuit, the first thing I did was I took the resistor, the base bias resistor from the positive going signal here, from this transistor here, I took that resistor out of here, completely out, and I allowed this here transistor to run full hard under the condition of this resistor being here for the base bias. And by doing that, I was able to take a voltage reading across the motor under that condition, and it went up to around 9 to 10 volts across there, so that we were getting a good heavy output of voltage across the motor. So I know then that confirms then that this transistor was not turning off far enough during the stall time to allow this to have that current flowing through there. So I know that I need to give this transistor more of a boost of signal current. When I put the resistor back in the circuit again and I stalled the motor, then we got the same outcome again, where this transistor here raised in voltage, but the motor voltage kept on going down yet because not enough signal current. So what that showed me was that the signal current, the motor current that's coming through here, that under a stall condition was enough to cause this transistor to detect that change and to cause an effect up here, but it was not enough signal current from the motor to cause this transistor to conduct less enough to the point where this can pick up more current for the motor. So what I needed was a signal amplification. This transistor needed to have some sort of an amplification of the signal coming in for it to be able to respond in a greater way for that. So now this is the circuit that I came up with. Again, we have the voltage regulator input on this side here. Everything just more closer together here. Now here's the feedback circuit that I have going on here. And I'm going to explain how I got these here values later on as well. But just to give a topology of how this is working. Under normal conditions, we know that the motor is running properly. We have proper voltage coming out through here and things like that working properly. Now when the motor stalls, we have a signal current from the motor now coming into this PNP transistor. This PNP transistor is in a common emitter configuration, so we have some current and voltage amplification of the signal into the base of this transistor here. And then this transistor here amplifies that because it too is in a common emitter amplifying configuration, and it further amplifies that signal. But let's take a look at where this transistor was coming in at and what we needed to do with this. Now back to the original circuit, we had this resistor right here, a grounding resistor to the base of this transistor that forms a voltage divider with this resistor here back to the positive output here. So we have this voltage divider here and the base current coming off that tap of the voltage divider at this point. So we need to cause this transistor to respond to a negative input from the motor to cause it to shut down enough to cause this to increase its output. So in order to do that, we need to reduce the resistance to ground to cause this transistor to shut down more. So what we need to do is, by changing this resistor and making that into a variable resistance, we can adjust the output of this transistor to cause the output of this transistor to increase as well. And so that's why we put a transistor in place of this resistor, as shown over here. So now, replacing that resistor with this transistor here, we now have an active resistance, a variable resistance that will respond to a input signal from the motor. Now again, the motor signal was not enough current to cause this transistor to respond great enough. But now that we have these two transistors right here, we now can have a great amplification of the motor signal currents to cause a greater output now here, to cause a change in voltage at this divider here that we were looking at, that this circuit can sense, that this transistor can sense that change at a greater value now and cause an effective change in here at a greater value. Now here's what we need. Since we have a negative signal coming from the motor to be inputted into this transistor, and we have a grounding resistor that needed to be replaced with a transistor, the best transistor to use for that would be an NPN transistor, because an NPN transistor can have its emitter grounded through a resistance and its collector at the voltage divider input here for the transistor. So that provides a nice variable resistance to ground for the base of this transistor. But now, since we have a negative input from the motor, the transistor can only turn on with a positive input, so we need a signal inversion, and so that's where this PNP transistor comes in now. So now the PNP transistor takes the signal from the motor, which is a negative signal, it inverts that signal and causes it to become a positive signal. Not only does it invert it, but it also amplifies that signal. So with this PNP transistor is acting as an inverting amplifier. So it takes the input signal from the motor of negative, amplifies it, inverts it, takes it to as a positive signal to the NPN transistor here. This transistor then takes that positive signal and it acts as a buffer amplifier. So that positive signal now becomes an amplified signal and this is another inverted amplifier. So it takes that positive signal and puts out a negative signal, because that's what the base of the transistor needs. The base of this transistor responds to a negative signal. So now we have this NPN transistor acting as another inverting amplifier. So now we have the signal coming in negative, coming out positive, and back out negative again for this transistor here, but now it's amplified twice. So the amplification of this motor signal now is the gain of these two transistor common emitter amplifiers. And that's why this transistor now senses a great change in motor current with respect to the original circuit, where it was only getting just a direct motor current. Now it's getting an amplified change of this motor current, and so it can respond in a more greater way, and that's how we get greater output here, and we get a change of motor voltage as well. And the motor voltage will actually increase now to the extent that we put a stall on this motor. You'll watch the motor, we'll put our voltmeter across here, and the voltage across the motor will now increase accordingly. And that's what I'll show you next on the circuit that I built now for this. Okay, just in case you're wondering why I didn't just take this PNP transistor and put that in place of the NPN transistor here, and then have the motor current come directly into that over here and eliminate one of these transistors. I tried that. I put a PNP transistor in place of this and just had the one transistor only. And the signal current from the motor just was not amplified enough from that PNP transistor to cause a great effect upon here to allow the motor voltage to increase. It just did not work properly that way there. It increased a lot more up here, but still not to the point that I'm looking for by having an increase in voltage across the motor itself. So by putting the NPN in between the PNP and this NPN here gives a greater amplification than the single PNP transistor would give alone. And that's the reason why I have to have these two transistors in here to increase the amplification greater. Okay, so now what I'll do is I'll show you the actual circuit working now. Okay, this is the circuit working with no motor feedback. I have the supply voltage here around 12, almost 13 volts, and this is the voltage drop across the motor itself, which I have hooked up here. And you can hear the motor running, and see it run. You can hear the motor running. And I'm going to put a stall across there now. Okay. Now I'm going to show you what it looks like when I put a stall across here. Okay, the voltage goes down to about there. Alright. That's with no feedback from the motor. Now I'm going to put the feedback in now. I now have the motor feeding back into the feedback circuit as we showed here. And listen to the motor now. As you can hear it, it's got some pulsing sound to it. Now again, there's my supply voltage coming in, and this is the voltage across the motor now, directly across the motor. I'm going to stall it here. Now I'm going to show what it looks like on the voltmeter. I'm going to start stalling the motor now. Starts out around 7. I put a stall in the motor, and it increases. Now if I bring it to a complete stall, about 7 volts. And the reason why again it drops back down again is because the supply voltage is dropping down on that regulator. But as long as we have a stall on here without any kind of total stopping the motor, the voltage will increase across the motor. Here goes the stall again. I'm going to put some load on the motor now. As I hold the load on the motor, I can keep it at 9 volts over 9.5 volts. Now I'm going to let go of the stall, and it runs back around 7 volts again. So the voltage is increasing across the motor. Also, listen to the motor sound. I'll explain that in a second here as well. Okay, so the first thing we did was we unhooked this wire right here and we ran the motor and we stalled it, and everything stalled across there. The voltage went down to about 4 point something. Then we hooked the circuit up, we hooked this wire back up here again, and we have now motor signal current coming through here. The moment I hooked this wire up, the sound of the motor became choppy. It began to get a different kind of sound. That sound is the sound of pulsating currents. What's happening is when that is being hooked up here, the motor is now constantly, signal is going back and forth here now. It's constantly readjusting itself up and down, up and down. It slows down a little bit and it brings it back up, slows down. It's constantly regulating itself now through this here loop going on here now. And that's why we have that pulsating current coming through the motor. Now it's not pulse width modulation or anything, but it is a pulsing current because the motor has to keep on going up and down in value of current to keep itself in equilibrium. And so when it starts to drop a little bit by any kind of natural means, it just picks itself back up again through this loop, and it's just a constant constant voltage up, or constant current flow up and down, pulsating through that motor. Okay, so now we've seen how a stall on the motor, a load on the motor, caused the voltage to increase across the motor, and that is my version of a torque control for the motor running. Okay, so next video now will be to improve the regulation of the main regulator here now with some feedback circuitry, and that'll be coming up next. But this video was a demonstration of how this feedback right here amplifies the change in motor current and causes that change to be great enough to cause the voltage across the motor to increase to give a better torque control for the motor now. Okay, that's all for now. Bye.